All right, guys, 1 o'clock, so we'll go ahead and get started. So last time we learned about Ksp and molar solubility. So we learned, although they're related, they're not exactly the same idea. So when we're talking about Ksp, does anybody remember the technical term for it? Solubility what? It's solubility product constant. It's not that important that you know the name. But the value of K here in our example of AB solid dissolving into A plus and B minus, what would the value of K be here? K equals what? Right, products over reactants. In this case, the products are A plus and B minus. And then do we put the reactants on the bottom? No, because they're solid and we ignore solids, right? So it does have to do with how much stuff got dissolved, but it's not the exact same as molar solubility. Molar solubility, on the other hand, is how much stuff got dissolved. So in this case is how many moles of AB got dissolved in 1 liter of solvent. How much or how many moles of AB got dissolved in 1 liter of solvent, right? Molar, moles per liter, solubility, dissolving stuff. So they're similar ideas, but they're not the same. And then previously in the chapter, I think 13, we learned that Q always goes to what? Q always becomes K, exactly. Q always becomes K. So you can see that we're not really learning too many new things. We're learning kind of the same thing again and again and again. We're just applying it to different situations. And so knowing the values of Ksp or molar solubility, you can predict whether things will dissolve or precipitate out of solution. So you can ask yourself questions of, will it dissolve / precipitate? And again, you can have an example of A, B as a solid dissolving into A plus and B minus. And you could have a Ksp which would equal some numerical value. And so asking, will something dissolve or not? Well, it depends on the current concentration, right? Depends on the current concentration. And when we're talking about current concentration or what our equilibrium is at a current time, what are we talking about? Q, exactly, Q. So we learned if Q is less than K, and here we're talking about solubility, but it's the same thing. If Q is less than K, is Q going to get bigger or smaller? It's going to get bigger because it's going to go towards K. So Q will grow. So if it's products over reactants, here we don't have any reactants. In order for Q to grow, what's going to happen to the concentration of A plus and B minus? They're going to increase. They're going to increase. So what does that mean? It means that we're dissolving more stuff. We're dissolving more stuff. So more solid will dissolve. If more solid will dissolve, what kind of solution do we have here? Do we have a saturated, supersaturated, or unsaturated solution? If more will dissolve. Unsaturated, right? If you're unsaturated, you can dissolve more stuff. If you're saturated, no more would dissolve, right? So this is unsaturated. When Q is equal to K, will anything happen to Q? Will anything happen to the equilibrium? No, it's already where it wants to be, so nothing happens. So if you add some more solid inside of a liquid and nothing happens, you know that your solution is what? Saturated, exactly, saturated. And then the final scenario, if Q is greater than K, what's going to happen to the numerical value of Q? It's going to decrease. It's going to decrease. So Q must decrease. And since Q is equal to the concentration of A plus and B minus, what's going to happen to the A concentration of A plus and B minus? They're going to get smaller. And if they're getting smaller, what's happening physically? Right? You're forming a precipitate. Stuff is coming out of solution. We're going towards the left side of the equilibrium, towards the solid. So we need less dissolved stuff. And so this leads to a precipitate forming. And so what can we say about the solution if it's just sitting there and solids coming out? What kind of solution is it? It's super saturated, super saturated. You have more stuff dissolved than your solvent can handle, so stuff is going to start coming out until Q equals K. Once Q equals K, you're going to be back to saturated. So let's see an example of this. We have magnesium hydroxide. I'm going to put it in some water. It'll dissociate into magnesium 2+, and how many hydroxides? 2 hydroxides. The Ksp of this is 8.9 times 10 to the negative 12. And so maybe a question that you're asked is, will a precipitate form when the concentration of magnesium 2+ is equal to 0.0537 molar, and the concentration of hydroxide is equal to 0.0010 molar. So we're asking, will a precipitate form or not? We're asking which way is the equilibrium going to shift. In order to figure out which way the equilibrium is going to shift, we have to know the end point, which we already know with a value of K, and then we have to know where we're currently at. Where we're currently at in our equilibrium is known as what? Q, exactly. So what we have to solve for here is Q. And Q, again, is the same as K, so it's going to equal our products. In this case, it's magnesium 2+ times what? Oh, concentration of hydroxide squared, exactly, squared. Don't forget the squared, it comes from this 2 in the coefficient. Now what do we do? Right, plug some numbers in and chug through. You have the concentration of magnesium, go ahead, plug that into there. You have the concentration of hydroxide, go ahead, plug that into there. And I got 5.4 times 10 to the negative 8. Is that what you guys got? Hopefully. Well, you know K is always products over reactants, so Q is always products over reactants, right? And then in this case, we're talking about solubility. The reactants are always a solid, so we always ignore them. So now we know Q, we know K. What do we want to do to the two? Compare them, exactly. So we have Q and we have K. Which one of these is numerically larger? One is 8.9 times 10 to the negative 12. One is 5.4 times 10 to the negative 8. Q is larger, right? And we always know that Q is going to go towards K. So in this case, Q needs to grow or shrink, right? Q shrinks. And so in order for Q to shrink, what happens to the concentration of magnesium and hydroxide, right? The concentrations decrease. And so what does that mean? That means that we get precipitation, exactly. So you had a supersaturated solution, and it's going to start precipitating out until it gets to equilibrium. There's some good examples in your book, 15.7 through 15.11 in the OpenStax book. They're a good example. Of this kind of stuff. But overall, it's the same thing we learned before. Q is going to go towards K. All right, so we know they both have to deal with solubility. Molar solubility and Ksp, they both have to do with solubility. But you can't actually go directly from Ksp to determine which one is soluble. Sometimes you can, sometimes you can't. So you can't use Ksp to say which compound is more soluble if the stoichiometry is not the same. So if it's not the same, you can't go directly from looking at KSPs and saying, oh, this one's more soluble, right? In general, bigger KSP, more dissolved stuff, more soluble. But the coefficients have to be the same. So let's take a look at an example of that. So magnesium hydroxide and iron carbonate, which one has the larger KSP? The iron carbonate. So if you're thinking about KSP as the amount of stuff dissolved, you think instantly iron carbonate is more soluble, right? But that's not always true. And that's because the coefficients are different. So if you look at the actual solubility, which one is more soluble? The magnesium hydroxide. Exactly. This one, although it has a smaller KSP, it actually has a larger solubility. Right? Why can that happen? Well, you have to think about what Ksp is here. Here, Ksp is magnesium 2+ times hydroxide to what power? Squared. Here, we have Ksp is equal to iron 2+ times carbonate to what power? To the 1 power, right? To the 1 power. So overall, this is to the 3rd power, while this one over here is only to the 2nd power. And remember, the amount in a pure solvent of water, the amount of magnesium or the amount of hydroxide is going to be equal to the molar solubility. Same for these two. But because you're raising them to different powers, they give you different numerical values. So if you want to see which one of these is more soluble and they have different stoichiometric values, if they dissociate into a different number of things, you actually have to go through the steps and calculate the molar solubility. What if they have the same stoichiometric values? If they both dissociate into 2 things, or if they both dissociate into 3 things, can you use Ksp directly? Yes, you can. Yes, you can. So you can use Ksp to say which is more soluble if the stoichiometry is the same. Because then their KSPs are going to be formatted the same, and thus the relationship between Ksp and molar solubility will be the same. So for example, here we have magnesium hydroxide and calcium fluoride. They're going to both dissociate into how many things? 3 things, right? So both of these KSPs are going to equal the concentration we'll just call X, that'll be the magnesium or the calcium, times the concentration of Y squared, right? They have the same format. And so here you can see it corresponds directly. Smaller Ksp, smaller solubility. Make sense? Yeah. You can try some, take some things, plug some numbers in, and you should see how the math works out so that they make sense. So again, there's a relationship between molar solubility and Ksp, but if the stoichiometry isn't the same, if they're not dissociating into the same things, it's not going to be directly. Okay? You can't just say, oh, this one's got a bigger Ksp, more soluble. You can only do that if they dissolve into the same number of things. Cool. So next up, we're going to learn about the common ion effect. So you guys saw some of this already when we did some of the labs, the equilibrium labs with the Le Chatelier's principle. Again, this is just kind of a rehash of Le Chatelier's principle. So you'll see what I mean by that. So let's take, for example, you have silver iodide. If you think back to Chem 101, you learned that this was insoluble. Now we just know that it's sparingly soluble or just slightly soluble. This can dissociate into silver plus and iodide minus. So what is Ag? Silver. Is silver cheap? No, silver is pretty expensive, right? There's jewelry made out of it. So let's say you had some amount of water and you know that there's silver in it, right? You want to make a bunch of money. So what do? You want to get the silver out of solution, right? Make it into a solid. That way you can sell it and make a bunch of money, right? So say you want silver iodide because silver is valuable, and you have some solution with silver in it. What could you add to make it precipitate out? Right. So if we want silver iodide, right, that's on the reactant side. So what could we add to push the equilibrium towards the solid? Right, you could add more silver, but that'd be kind of dumb because then you're kind of back to square one. What else could you add? More iodide, right? Remember Le Chatelier's principle. When we add a product, which way does the equilibrium shift? Towards the reactants. So if you want the silver out of here, you just add a bunch of cheap iodide and your silver iodide will precipitate out. You can then, collect that, reduce it down to pure silver and make some money. Right, so you could add iodide. And again, this is just a rehash of Le Chatelier's principle. So I'll just write Le Chat. Right, so AgI dissociating to Ag plus I minus. If we add I minus, right, maybe that's from potassium iodide, sodium iodide, something cheap. Iodide's pretty cheap. We're going to cause a shift in the equilibrium. And in which direction is the equilibrium going to shift? Towards the left, right? Towards the reactants. Equilibrium shift, and so you get more solid silver iodide. So again, just a rehash of Le Chatelier's principle. But here we're seeing we can manipulate the equilibrium of a chemical reaction to get what we want, right? That's what chemistry is all about. You learn some facts and then you learn how to manipulate them to get to where you want to go. Something else that we saw in the Le Chatelier's lab is we added acid and base, and that also shifted the equilibrium. So H plus and OH minus can also be common ions. Yep.
What do you mean by common ion?
So a common ion is something that your thing is dissociating into, and it dissociates into it. So iodide or silver would be a common ions of this. Something like fluorine, bromine, they would not be common ions. So we'll see examples of what are common ions and what aren't in a little bit. So for example, we have magnesium hydroxide. And dissociate again into magnesium and 2 hydroxides. So when we change the amount of H plus or OH, what are we changing about the water? It's the technical term for it. The pH, right? The pH. So we can take a look at a situation of a high pH. High pH, if we want to increase the pH, are we adding acid or base to that? Base, right? So you're adding base. And so what about your concentration of hydronium? Is that high or low? Or hydroxide? Hydroxide. Hydroxide is high. Hydronium will be low. Where do we see hydroxide in our equilibrium? On the products side, right? On the product side, dissolved hydroxide on the product side. So when we add hydroxide, which way are we going to shift our equilibrium? Towards the left. Towards the left. So that's an effect that you saw. Sometimes you made the solution basic and you saw precipitation occur. So the opposite of a high pH would be low pH. You would be adding a lot of acid. And when we think about acid, we think about H+, right? Do we see H+ in our equilibrium? No, we don't see H+ in our equilibrium. So it's not going to have an effect on our equilibrium? Not necessarily, it will. What will H+ interact with? The hydroxide. To form what? To form water. So when we add acid, what are we doing to the concentration of hydroxide? We're decreasing it. We're decreasing it. In this case, hydroxide is a product, so we're decreasing the amount of product. Which way are we going to shift our equilibrium? Towards the right, towards the products. Exactly. So if you want magnesium hydroxide to precipitate out, make it basic. If you want it to dissolve, make the solution acidic. So let's take a look at an example. What is the effect on the equilibrium of aqueous magnesium hydroxide when we do some stuff to it? So again, we have magnesium hydroxide dissociating into magnesium plus 2 hydroxides. And we're going to add some stuff to it. The first one, we're going to add some magnesium chloride. Then you're going to add some potassium hydroxide to a separate solution, some sodium nitrate, some magnesium hydroxide, and some hydrochloric acid. So go ahead, take like 2-3 minutes and tell me, when you add this stuff, which way is it going to shift the equilibrium? Will you get more precipitate or less precipitate? Nothing happening is always an option, yep. Unfortunately, in chemistry, when you're trying to do research, that's the most common thing that happens. Do a whole bunch of work and you get nothing.
Right, I know that. I'll just go to the right. I know that. I was wondering, like, when they add these things at thoughts, they add in like things already associated. And then they add in, it's like they're gonna add in I know what you're saying. I'm wondering when they're gonna add it. Whether they add it when it's associated or before that. On the right hand side, they added the MG2OH. They were adding more solid. No, I don't know. No, shift to the left is the MGOH2. Yeah, I don't know how it works though. It's just gonna dissociate more. It's gonna that means you have more products. The product is shift to it won't shift to the right. I just think it's gonna give you more. I'm thinking that you add more reactant. You add more of that when it's gonna dissociate. Yeah.
All right, so let's take a look at this. So when we add magnesium chloride to the solution, what's that going to dissociate into? Magnesium 2+ and what else? Right, and some chloride minus. Do we see either one of these on either side of our reaction? Yeah, we see the magnesium 2+ on the product side. According to Lachey's principle, when we add more products, which way does the equilibrium shift? Towards the reactants, exactly. So this way is going to go left, right? Because magnesium is a common ion, it's going to have it precipitate out. When we add KOH, what's that going to dissociate into? Right, potassium and hydroxide, right? Do we see potassium or hydroxide anywhere? Yes, which one do you see? Hydroxide. Again, are we adding a reactant or are we adding product? Product. So which way are we going to shift? Towards the reactants. Exactly. Next up, we have sodium nitrate. What's that going to dissociate into? Na+ and what else? NO3-. Do we see that anywhere? So it's not a common ion, right? So is that going to do anything? No. So nothing happens here. You've added something that isn't part of your equilibrium. Now we have magnesium hydroxide. Is that a reactant or a product that we're adding? It's a reactant, right? Reactant. So which way is that going to shift? Towards the products. Towards the product, right? If you don't, as long as you don't have a saturated solution, if you pour some salt into water, what's going to happen? It's going to dissolve into Na+ and Cl-, right? It's going to dissolve and dissociate. That's going to happen up until you're saturated. When you're saturated, then nothing happens. Question?
So these equations, are they already saturated?
You'd have to read the question. We're going to assume that they're not saturated.
For me, I thought with the MgOH2, right? So you add it, so I'm wondering, like, where do you add it? Do you add it to the, like, when the things are already separated?
Well,
what's when you separate more, have more products, or shift to less?
No, yeah, I see what you're saying, but when you're adding the solid magnesium hydroxide, what you're adding there is a reactant, right? It'll shift towards the product side of things.
Are you adding it like when it hasn't separated or before that?
Well, you can't add it after it's separated because that doesn't really make, you know, you're adding solid sodium magnesium hydroxide. So I probably should have put a little solid here. Does that help?
Yeah.
Yeah. All right. HCl, what's that going to dissociate into? H+ and Cl-, right? So that doesn't have any common ions, so it's not going to do anything, right? No, wrong, right? What's the H+ going to do? It's going to react with the hydroxide, exactly, to form water. And so in effect, what are we doing to the concentration of the hydroxide? Decreasing it, right? So hydroxide is a product, so we're decreasing the amount of products. So which way is this going to shift? Towards the products, right? So you see how you guys kind of already knew this information just based on our previous discussions of equilibrium. It's just now applying it to new things.
Your arrow is that it's decreasing the product of the OH, right?
Yep.
But why does your arrow go then for the product?
Because if you decrease the amount of product,
oh, yeah,
you've got to go towards it. Yeah. You got to be careful. The decrease, increase. Yep. Cool. So one way to have these questions is to, which ways the equilibrium is going to shift, right? But that's obviously not good enough. We want to know how much stuff are you going to have at the end and a numerical value for that. So a question you could see is something like calculate the molar solubility of cadmium sulfide in a 0.010 molar solution of cadmium bromide. So you'll see a good number of these types of questions in your homework. There is an assumption that you have to make. And the assumption is that whatever they give you that's already in solution, you have to assume that it's a strong electrolyte. What does that mean? It's going to completely dissociate, right? There's no K there. It's just completely one way. So if you have 0.01 molar of cadmium bromide, you have 0.01 moles of cadmium and 0.02 molars of the bromide, right? So you have to assume it's a strong electrolyte. And then the question also gives you that the Ksp of the cadmium sulfide is equal to 1.0 times 10 to the negative 28. Right, very small number, something most people consider insoluble. Yeah, so it's asking you to calculate the molar solubility. The molar solubility is how much stuff can you dissolve. So you're going to assume that you're going to add you're going to add excess, and then it'll reach equilibrium. So if we take a look at cadmium sulfide, we're trying to dissolve it. So let's take a look at what it's going to dissolve into. What's cadmium sulfide going to dissolve into? Cadmium what? 2 plus. And sulfur what? 2 minus. Right. And then you don't know what's going on in this class, so what should you try? A rice table. What do I do with the cadmium sulfide side of things? It's solid, right? So we ignore it, right? The cadmium sulfide is solid. When we're talking about dissolving things, we really just care about the stuff in solution. So now normally here I would just put 0 for both things. But do we have 0 of both things in solution currently? No, we already have some cadmium bromide in solution, which means we already have some cadmium in solution. So what's our current concentration of cadmium right now? Right, 0.01. What about the sulfide? Is there any sulfide in cadmium bromide? No, so we can leave that as 0. These two, the change then becomes what? Plus x, right? Both of them have a coefficient of 1, so they're just both plus x. So then this one becomes 0.010 plus x. This one's just x. So you set up your rice table. What do you do now? Right, set it equal to this Ksp. Ksp is going to equal what times what? Right, it's going to be equal to the products, right? So cadmium times the concentration of sulfide. In this case, we know that this is 0.010 plus x times x. We can take these numbers and plug them in. And we know Ksp is also equal to what value? Right, 1 times 10 to the negative 28. Now we just have to solve for x. But what can we do to make our life simpler? Right, we know that K is small. So we know x is small. And so we know the 0.01 plus x is going to be approximately equal to what? 0.01. So then we can just say 0.010 times x is equal to 1.0 times 10 to the negative 28. You really shouldn't even need a calculator for this. It's 1.0 times 10 to the negative 26. Right? But you can use a calculator. It's not a math class. Don't worry about it. So did we answer the question? What does the question ask for? Calculate the molar solubility. So we have to think about how many moles of stuff got dissolved. So what's that value going to be equal to? How much of our cadmium sulfide got dissolved? Is that going to be equal to this 0.01 plus x? No, because that includes the cadmium that was already there. What about just this x? Where did all this sulfur come from? The cadmium sulfide. Thus, for every 1 mole of cadmium sulfide that gets dissolved, we get 1 sulfur. So for every sulfur that we have, 1 cadmium got dissolved. So in this case, it'll be equal to x. But you have to pay attention to your stoichiometry. If you set it up this way, it should always equal to x. But if you start doing the ice table in a different way, it might screw you up. So just think again, what is molar solubility? How many moles per liter of this stuff did you dissolve?
Like that in sulfide, it was like for some reason sulfide was 2. Would you say that for every 2 atoms of sulfide you have 1 cadmium?
Yeah, exactly. In that case, so it would still be equal to x, not 2x. Exactly. So as long as you set up this ice table this way, it'll always end up being x, but some of you guys like to do your own thing, that's fine, as long as it works. Right, so you know your molar solubility of cadmium sulfide is equal to the concentration of the sulfide, because that's the only place where the sulfide could have come from. There was no sulfide in the water already, and so it had to come from there. And you know it's a 1-to-1 relationship, so you know this is equal to x, and thus your molar solubility here is 1 times 10 to the negative 26 molar. Make sense? I posted the homework this morning, so you can see some examples. I try to go through the notes, and I'm trying to do a better job of having the homework go in the exact same order as lecture does. So you can see, oh, we haven't covered this question. That means we haven't covered the rest. It's not perfect yet, but it's getting better. All right, so we can use this common ion effect to precipitate out things that we want. And so this is known as selective precipitation. I think the open stacks gives like a good example. It's like a waste treatment plant. So how do they, you flush your toilet, they clean that water out, and then, next day you're drinking that water again. How do they get that stuff clear? A lot of it is through the selective precipitation. Right, so you have some water in here, and let's say you had some magnesium 2+ and some calcium 2+, right? Your water has some magnesium and has some calcium. Well, if we want magnesium 2+ to precipitate out, because we want to separate them. For whatever reason, we want to separate our calcium and our magnesium. If we wanted to do that, we just have to find some other counter ion to add that will make the magnesium insoluble while keeping the calcium soluble. So you need to find something that will precipitate out one cation, but not the other. And so to kind of figure that out, you can use KSPs to help you. You can go up in some kind of manual, look up different values of KSP for magnesium and calcium compounds, and find one that will precipitate out one but not the other. So for example, our previous example, magnesium hydroxide. This KSP 2.0 times 10 to the negative 13. And then calcium hydroxide, Ksp is equal to 4.86 times 10 to the negative 6. So can we compare these Ksps directly to talk about solubility? Yes, they both dissociate into three things, so their stoichiometry is the same, so we're good. We don't have to go calculate molar solubility because it's going to be directly proportional. So we have the same stoichiometry here. And which one of these is smaller? The magnesium. The magnesium is much smaller. The Ksp of the magnesium hydroxide is much smaller. So if we slowly add hydroxide, which one of these is going to precipitate out? So we slowly add hydroxide, right? Both of these values are going to be equal to the concentration of calcium times the concentration of hydroxide. So when you start adding hydroxide, our Q is going to start growing, right? It's going to start at 0 and it's going to start growing. When it starts growing, which one of these two numbers is going to hit first? If you go from 0, which number are you going to hit first, 1 or 10? 1. You're going to hit the smaller number first, right? If you start from 0 and you grow, you're going to hit a smaller number before you hit a bigger number. So which one of these is the smaller number? Exactly, this magnesium hydroxide. And once Q becomes greater than K, because it grows too large, what's going to happen? It's going to precipitate out, right? Q is going to have to shrink, so it's going to precipitate out. So which one of these two is going to precipitate out first when we add the hydroxide? The magnesium, right? You think about Q, it's starting at 0. You're going to add the hydroxide. Both of them have hydroxide in there. Q is going to start growing. It's going to hit this K first. And so precipitation is going to start occurring. So slowly add hydroxide and you get magnesium hydroxide to precipitate out first. All right, let's draw a little picture of that. All right, you end up with a solid of magnesium hydroxide. And your calcium will stay in solution. Again, this is the kind of theory about it, just kind of logically thinking it through. Not good enough. We want to know exactly how much hydroxide do you have to add to get this magnesium to start coming out. So let's take a look at it. So in seawater, the concentration of magnesium 2+ is equal to 0.059 molar, while the concentration of calcium 2+ is equal to 0.011 molar. The question is, what pH begins the precipitation? And then another question is actually the first question that you really should answer is, what precipitates? And for magnesium hydroxide, the Ksp is 2.06 times 10 to the negative 13. And for calcium hydroxide, it is 4.86 times 10 to the negative 6. Exactly. If you add too much hydroxide, you're going to force both of them to come out. So you want to add just the right amount to have the magnesium only come out.
Wait, so that's the way they determine how, like, the concentration of certain, like, of substances and, like,
No, at this point, we just use spectroscopy. Basically, we can use instruments to tell us the instant concentration of something. But say this wasn't magnesium. Say this was something dangerous like lead in the water. How do you get the lead out? Well, something like lead chloride is insoluble, so you could add salt, NaCl, that'll precipitate out lead chloride. And now you've got a little extra salty water, but at least it's, doesn't have lead in it. Cool. So what's true about the stoichiometry of these two? Right, they're the same stoichiometry. Which concentration is higher? Which concentration is higher? The concentration of magnesium is higher than the concentration of calcium. So Mg2 plus is higher concentration. And what about the Ksp? Which one is, do we want to look at which one's smaller or which one's bigger? We want to look at which one's smaller. So which one's smaller? Right, and the magnesium hydroxide is smaller. Ksp is smaller. And it's significantly smaller. The difference between -13 and -6 is about 10 to the 7. 10 to the 7 is what? 10 million? Right, so it's 10 million difference. So it's quite smaller. So to ask our first question is, which one's going to precipitate out first? Right, the magnesium hydroxide is going to come out first. It's in a higher concentration. Its K is lower. So once we start adding hydroxide and Q starts growing, Q is going to equal K for magnesium much faster than it's going to equal that of calcium. So magnesium hydroxide will come out first. And at what point will it come out? At what point does precipitation start to occur when we're talking about K and Q? Right, when Q is, we're going to say when Q is equal to K. Technically, you're right, it's slightly above, but it's like infinitely smaller, infinitely slightly above. So it's essentially when they're equal. So we're going to say will precipitate out when Q is equal to K. So do we know the value of K? Yeah, it's given to us right there. So we want to find when Q is equal to K. Are we changing the concentration of the magnesium? That's kind of fixed already, right? What we're talking about is the pH. So pH, we're talking about how much acid or base we're going to add. So in this case, we know that K is equal to the numerical value of 2.06 times 10 to the negative 13. And the solubility product constant is always the product of the stuff that's dissolving, right? So it's going to be equal to what? The concentration of what? Right? Magnesium 2 plus times the concentration of what? OH minus squared. And our question asks for pH. In order to get pH, we have to know the concentration of H plus or POH. In order to get there, we have to know the concentration of hydroxide. So what we're after here is the concentration of hydroxide. So do we know the concentration of magnesium? Yeah, it's given in the problem. We know the value of K, so can we solve for the concentration of hydroxide? Yeah. Yep, exactly. So 2.06 times 10 to the negative 13. Next thing you'd want to do is solve algebraically. So divide both sides by 0.059 and then take the square root of both sides. What do you get? There we go, 1.9 times 10 to the negative 6, yeah?
Then you get a minus log 8.
Yeah, we'll get there, we'll get there. So when we have our concentration of magnesium equal to 0.59, and we know K, hydroxide must be 1.9 times 10 to the minus 6 in order for Q to equal K. And that's when precipitation will start occurring. But again, our question doesn't ask what's the concentration of hydroxide, how much hydroxide you should add. It asks for the pH. So we got to get there. So we know that POH is equal to what? Right? Negative log of the concentration of hydroxide. We have the concentration of hydroxide, so we can plug that into there. And you get what numerical value? .72, right? You get a POH of 5.72. Does it ask for POH? No, it asks for pH. Generally, we talk about pH. So we know that pH plus POH is equal to what? 14, right? And so then we can plug this in for POH, solve for pH to get a numerical value of what? 8.28. So the magnesium hydroxide will start precipitating out once you hit a pH of 8.28. I would say similar to the acid-base stuff, at first look, this might look kind of confusing, but once you kind of reread the notes and let it sink in a little bit, you'll see, oh, wait a second, I'm just kind of doing the same thing again and again and again. The other trick here is being good at word problems, right? Taking the word problem, trying to figure out what it's asking of you, and then taking that information, what information do you need, what information do you not need, and coming up with a plan. And unfortunately, the only way you get good at that is through practice, right? There's no kind of quick way to it. So selective precipitation is used to make stuff precipitate out when you want it to precipitate out. Another thing it's used for is questioning whether you have something in solution. So for example, if you know silver iodide is insoluble and you have a solution and you're wondering, does this have silver in it? Well, you could add some iodide in there. If something comes out, then yeah, you had silver. If something doesn't come out, then no, you didn't have silver, right? So this is what we're going to be doing in lab later on. It's called qualitative chemical analysis. Right, so a big question in chemistry is you can't see this stuff dissolve. So a big question is, what do you have in the solution? One way to figure it out is to add some stuff in there and see if something comes out. It's a bit more old school way. That's what we're going to do in lab. So it's going to be approximately the last 4 labs. So we're going to do this approximately 4 different times, with the last lab being kind of like a final type of thing. You'll be given an unknown solution and asked, what's in here? And you're going to have to design your own experiments to figure out what's in here. And you're going to use this selective precipitation idea to do so. So what you're going to have is you're going to have solutions of unknown cations. So we're just going to do cations. And then you're going to figure out how to see if you have something or not. So for example, you might be wondering, do I have silver in here? Well, you could think, and you're like, well, wait a second. In Chem 101, I learned that silver chloride is insoluble. Now I've learned that it's actually not technically insoluble, but it's still, the solubility is still very, very tiny, right? So this is very small. So if you add an excess of chloride, if silver is there, what's going to happen? You're going to see a precipitate. If silver's not there, what's going to happen? Nothing. You won't see a precipitate, right? So if Ag plus is there and you add chloride, silver chloride will precipitate out. Yeah, that's exactly a good question. So just because you see a precipitate, you're like, I could have silver chloride, or it could be some other chloride that's insoluble. Exactly. So what we'll see in lab is we're going to do multiple tests. So you'll see a precipitate and you'll be like, okay, now I got 1 of 10 things. Now I got to do another experiment. I got 1 of 5. And then in real life, obviously, it's not as controlled, so it's even more complicated. But actually less complicated because in real life, you just use an instrument, click some buttons. All right, so here's what this kind of picture is showing. It's just the selective precipitation, qualitative chemical analysis type of thing. And we'll be practicing this in lab quite a bit. So here in the beginning, you have a mixture of cations. You're going to add something that makes one of the cations insoluble. You're going to take that out of solution, and then you're going to continue on and precipitate out the other ones. It's a way to separate the cations from one another. Here's kind of a list of rules, essentially. Yeah, once it precipitates out, you can decant or you can just filter. It's not hard to remove or separate a solid in a liquid, right? So like someone just pointed out, it's not just going to be one thing that comes out of solution. So for example, there's different groups of cations that are based on their properties. So you can see in the first one, silver, lead, and mercury. When we add 6 molar hydrochloric acid, what we're really talking about is the chloride. And so you get a bunch of insoluble chloride salts. So silver chloride, mercury chloride, lead chloride, and CHEM101, you learned those are insoluble. So when you add HCl, you're adding Cl minus, you're shifting the equilibrium towards the left, towards the solid, and you get these guys to precipitate out. And then you have another group and another group and another group, and you can do different things. You can add different anions to make them precipitate out selectively. And so in the end, you can separate the solution. I don't expect you guys to memorize this chart or anything. It's just kind of a preview of what we're going to do towards the end of the class, but we're going to kind of learn the content now, and you guys will apply it later. It doesn't match up perfectly, unfortunately, but good enough. All right, so we learned about precipitating stuff out, but when you add some stuff together, you don't always get a precipitate. There's other options of what you could get. And one of the things you can get is what's known as a complex ion, or really a coordination compound. Coordination compound is more often used than complex ion. So sometimes when you mix 2 cations and anions, nothing happens. Sometimes you get a precipitate out. Sometimes you form a coordination compound. And coordination compounds or complex ions are Lewis acid-base adducts. So last time we said when we're talking about Lewis acids and bases, are we caring about H+? No, what do we care about? Electrons. And we said acids are what? Electron pair acceptors. Exactly. When an acid donates an H+, it takes those electrons from that bond to itself. So it's accepting those electrons. So it's an E- pair acceptor. And thus the base is what? E- pair donor. So when we're talking about these coordination compounds, the vast majority of the time we're talking about using transition metals. And transition metals are Lewis acids. So they're accepting the lone pairs. And then, of course, if you have a Lewis acid, you have to have something giving it these electrons. In order to donate an electron pair, you have to have an electron pair. And so acid Lewis bases are molecules with lone pairs. So molecules with lone pairs, something like NH3 has a lone pair, something like hydroxide has a lone pair, something like chloride has a lone pair, something like cyanide has a lone pair. And of course, there's many other examples. And these guys are going to be what? Lewis acids or Lewis bases, right? Lewis bases. So these molecules are often Lewis bases. When they're bound to a transition metal, they are also called ligands. You'll hear ligands much more often than you will hear Lewis bases. And we'll learn more about this stuff when we get to the transition metal chapter. This stuff is very important for like catalysis. So for example, you could have silver, and you could have two ammonias, two NH3s, and they will form this coordination compound. So the electrons from the NH3s will donate to the silvers. And notice now that the charge from the silver we say is delocalized over the coordination compound, but the charge doesn't change. So is silver here going to be the Lewis acid or the Lewis base? It's accepting the electrons. That's the acid. This is a Lewis acid. And that makes ammonia what? Lewis base. And that makes sense. Even when we're talking about Bronsted-Lowry, ammonia NH3, it's a base. It's still a base, right? They're still kind of one and the same. It's again, all squares are rectangles, but not all rectangles are square type of thing. So you can call this a Lewis base. You could also call it a what? A ligand, right? Or a ligand. Ligand? No, I've always heard ligand. I know I think in ligand, I think that's biology. Yeah. It's in chemistry, it's ligands. I think they're referring to different things though. Yeah. We're right, they're wrong. And so this forms a complex ion, or more often called a coordination compound. And so what kind of arrow do we have here? Do we have a one-way arrow? No, we have an equilibrium arrow. And if we've got an equilibrium, what can we write? A K. We can write a K for this. But again, it's the same idea. This is called a KF. And it stands for, get this, formation constant, because you're forming this thing. Right? And even if you don't know anything about Lewis acids or bases, if I give you the above chemical equation, should you be able to figure out what K is? Yeah, right? It's always going to be what over what? Products over reactants. In this case, our product is going to be our coordination compound. Over top of our reactants. In this case, the silver. No, it's anything that has a charge can't be a solid. Can't really be a solid. Yeah, these are all aqueous solutions. Times what? The NH3 squared, the ammonia squared. Right. So again, we kind of learned something new, Lewis base adducts, but the K is not really anything new. And this next part isn't really anything new. if we have a large KF, what does that mean? Right, they're more product. And so basically what it means is that the coordination compound is favored, right? A large K, you're going to go more towards product. In this case, it's the coordination complex. So that means that this coordination compound is very stable. It's very good. You're going to have a lot of it. We'll learn about energy in the next chapter. We'll learn about why is this K big? Why is this K small? That's coming up. So coordination compound is more favored. And so you can look up tables of this stuff, and you can see different values of different KFs to form different coordination compounds. So you can just see some examples. You can see you always have a transition metal and then some kind of Lewis base that has electron pairs to donate, right? You can't be an electron pair donator if you don't have any electron pairs to donate. Let's see, can we can do it. All right, so again, we're going to rehash a different topic back from chapter 14, I think, and kind of what we've seen with this Lachey's principle with the H plus and the OH minus, right? And what you saw in the lab. Even though you draw one equilibrium reaction, it's not by itself. Everything exists, with other stuff. And so equilibria are not by themselves. If you shift one equilibrium in a solution, that'll shift another, that'll shift another, that'll shift another, right? They're all interconnected. And so we called those, if you remember, coupled equilibria. In this chapter, there's not really too many homework problems about this stuff, so you want to review from chapter 14. It's the same idea. I'm just going to show you some kind of cool examples of it. And so again, things generally aren't pure. So you're not looking at a situation where you just have A going to B. You have other stuff in there that messes with things. And so if you have a mixture of things, you're going to have a mixture of equilibria. Right? And I like to compare, it's like an ecosystem. Right? You change one little thing about an ecosystem, it has drastic effects. So, for example, we have silver chloride. And as we saw, the solubility product constant for silver chloride is very small, meaning that it's generally thought of as insoluble. Well, what if for whatever reason you had some solid silver chloride and you wanted to make it dissolve? Well, maybe you could add some ammonia to this, because ammonia and silver will form a what? Right, a complex ion or a coordination compound, like we saw from the previous example. And this coordination compound will indeed become soluble. So you'd have to have some chemical intuition, or you'd have to take a look at some kind of table like this. So you can see right here, silver and ammonia. The KF's pretty big, it forms some kind of thing. But yeah, if you have some kind of Lewis acid, something that accepts electrons like a transition metal, and a Lewis base, something that has lone pairs to donate, they're going to react somehow. How much they're going to react, you'd have to solve empirically or experimentally or pull it from a table. And I drew this little aqueous symbol because this stuff is indeed thought of as soluble. But you don't want to start experimenting without knowing what to expect. And so you want to see which way is this equilibrium going to be favored. Are you going to get more of the solid to the left, or are you going to get more of the aqueous solution to the right? Well, the ratio of products to reactants is K. So what you want to know is you want to know the value of K. So the question that you're asking yourself is, if you add ammonia, which is NH3, to a solution with solid silver chloride, will it dissolve? And again, this depends on this K. If we have a large K, what does that mean? It's going to be more soluble, right? Large K favors the products. In this case, the products are soluble. So large K is that this silver ammonia is formed or favored. And so it's soluble. What if this K value is small? Which side is going to be favored? The reactant side. In this case, that's the solid. Favored just means which side is they're going to be more of. Yeah. Well, you could do this experimentally, but maybe you don't have some silver on your hand. You don't want to buy a bunch of stuff just to find out that it doesn't work, right? So you're going to put some thought into it and do some background stuff. So you can solve if you know some things. For example, if you know that silver chloride dissociates into silver and chloride with a Ksp of 1.77 times 10 to the negative 10, right? That tells you how soluble this silver chloride is. And then the other component that you're looking at is the formation of the coordination compound. So you could take a look at that as well. And you know this Kf is equal to 1.7 times 10 to the 7. So let's take a look at our overall equation and take a look at what we know, right? We have this overall equation that we don't know. And we start off in this overall equation with this silver chloride. In the stuff that we do know, where does the silver chloride show up? Right. In the first equation, right? In the first equation as a reactant, right? Silver chloride dissolves into silver and chloride, right? Next up, we have ammonia. Where do we see ammonia? Reactant in the second equation, exactly. Next up, we have this silver ammonia coordination compound. Where do we see that? As a product. And then finally, we have this chloride minus. Where do we see that? The products of the first equation. So one thing we can try to do is we can try to add these two and see what we get. When we add these two, what's going to happen to the silver plus that's on both sides of the equation? They're going to cancel one another out. And then when that happens, we get AgCl plus this ammonia is in equilibrium with this coordination compound and chloride, which if we take a look at that equation, Does that look like the same equation that we want to solve for? Yes. And so blast from the past, when we add two equations, what do we do to the K's? We multiply them, right? And again, you can write out the K products over reactants to show you mathematically why it works out. You want to review that chapter. I'll show you some more examples. There's not too many homework stuff in it, so you want to go back to that chapter and review it. So we multiply these K's, and when you multiply these K's, you get 3.0 times 10 to the negative 3. So overall, still not great, but it's more soluble than regular old silver chloride, right? We went from 10 to the negative 10 to 10 to the negative third. That's 10 to the 7 difference. So that's about 10 million times more soluble, right? The silver is 10 million times more soluble when you add the ammonia than when you don't. So still more soluble than AgCl. And again, remember when we add equations, we multiply K's. So here's a picture of that. So in this above picture, you've got some solid silver chloride down in the bottom, and you want to dissolve it. So up top, you're going to add some ammonia. And when you do so, you're going to form some of this coordination compound. And this coordination compound is soluble, so your stuff will dissolve. And so this is something you guys are going to see in lab and do at the end. You're going to make a solid, you're going to precipitate some stuff out, but then you're like, I want it to dissolve back in, because now maybe you precipitate out two things. You want to selectively redissolve one, so you can add some type of Lewis base to form some kind of coordination compound and redissolve it. It's actually chapter 13, chapter 13. So put a little star here, right? Review chapter 13 for the coupled equilibria. We'll see some more examples tomorrow or next class as well. And that's it. See you guys in lab.